Hi, good morning, everybody. Welcome to Friday at reInvent. My name is Saji Matthew. Along with Austin Fonancier from Spokeo, we're going to be doing how Spokeo improved web application response times with Amazon Elastic File System. So we have a packed session for you. Austin's going to dive in to the details of the Spokeo use case, but I know there's probably a number of you in the room who may not be familiar with EFS, so I'm going to give a brief and gentle overview to the service. So to understand EFS, it's important to understand how storage fits into the Amazon platform. Coming into this week, Amazon had a wide array of services, the most depth and breadth of any cloud platform out there. And as you saw the last couple of days, we even added even more services to that. So storage on AWS can be categorized into a number of different areas. So we have file, which is represented by EFS. We have object storage, which is represented by S3 and Glacier. S3 is one of our older services. The scale, the performance is something that is unparalleled. And generally, S3 can be used for any type of use case where web object storage is appropriate. Glacier can be used for things like long-term archiving for objects that are infrequently accessed. We have block storage, which is used by Amazon EC2, and block storage is represented by EBS as well as EC2 instant storage. EBS provides persistent block storage. EC2 instant storage provides temporary or ephemeral storage. In addition to that, we have a variety of ways to import data into the AWS cloud. Prior to this week, Snowball enabled you to import petabytes of data, but as you saw on Wednesday with Snowmobile, you can now import exabytes of data. In addition to that, services such as Storage Gateway enable you to synchronize data between your premise as well as AWS. Direct Connect gives you high bandwidth, low latency network connectivity from your network to the AWS cloud so you can transfer data through the network. In addition to that, we have Kinesis Firehose, which enables the transferring of or streaming of massive amounts of real-time data to various AWS targets. So as we go through the presentation, keep in mind how EFS fits into the big picture of all this. You have a lot of different storage options, and EFS is a storage option when you need a shared file system that can be leveraged by many different, or thousands, or hundreds of thousands of different EC2 instances. So why did Amazon create EFS? Well, primarily, it's the same reason we develop any new service, and that's because we want to alleviate the burden of managing infrastructure from you, the customer. So depending on your role, you may be familiar with some of these issues. So for example, if you're an IT administrator, one of the problems that you often encounter when you want to set up a new piece of functionality is that you have to procure hardware, set it up, maintain it, make sure there's enough space, heating and cooling. It's all the stuff that you have to deal with when you have to deal with infrastructure on premise. You also have to think about how much demand there really is for this particular functionality within the organization. And forecasting demand can be very, very tricky. Often it's guesswork. If you're an application owner or developer, you may be constrained by lack of storage space. And so things that you may want to get done may have to wait until IT provides that service to you. If you are a business manager, you are constantly in the cycle of refreshing the hardware and upgrading it. The other big problem is that with typical hardware, well, there's a lot of CapEx that you have to expend up front. So what if we could eliminate all of those issues and make it easy to consume a shared file system? So what Amazon's done is basically eliminate any sort of management and maintenance related to a shared file system. And it's a shared file system, as we'll see, that can scale into the petabytes. If you're an application owner or developer, EFS will simply work with your existing applications. And more importantly, you never have to wait for IT to provide the storage that you need. If you're a business manager, you can trade CapEx for operational expense and pay as you go. So you simply pay for the storage that you use on EFS. You don't pay for any provision storage. We'll talk a little bit about that later on as well. Overall, for everybody involved, it means less time and effort managing a file system infrastructure. So what is Amazon Elastic File System? It is a fully managed file system for EC2. So when we say fully managed, that means there's really no work on your part to actually create or maintain the file system. It's all done for you. All the complexity, the durability, the reliability, the scalability is all taken care of for you. It's done on the back end. You, the customer, simply create the file system, which takes about a minute. And then from then on, you can start using EFS as you would any shared file system. Your applications that call into the file system will simply work. EFS today is based on NFS, so any application that can talk with the NFS APIs or file system APIs can simply work without any sort of compatibility issues. EFS can be shared amongst thousands of instances, so it can really scale. So if you have a small workload that eventually may grow into a much larger workload, EFS can grow with you. There's never any reason to provision storage on EFS. You simply create a file system, and as you'll see, you'll have a lot of space available to you, and you simply start adding and removing files, and EFS will grow and shrink with you. It's highly available and durable, and this is one of the most important features of the service. Making a service durable and scalable and reliable is really complex and difficult. And the EFS service abstracts that away from you, the customer. You simply start using it, and we'll see how the availability is implemented in just a few slides. EFS also provides strong consistency. That means consistency in terms of performance as well as file semantic consistency. So there's four main areas or advantages to EFS. First and foremost, EFS is designed to be simple. As you'll see in a couple of slides, you can create a file system in seconds. And then once you mount it, which takes another few seconds, you're ready to go. That's all there is to it. There's really no management on your part at all. It seamlessly integrates with NFS or any application that's using NFS or any operating system Linux operating system that can understand NFS. And the pricing is very, very straightforward. It's basically the amount of storage that you use per month. There's no request charges or I/O charges or anything like that. EFS is designed to be elastic. What this means is that the file system can grow and shrink as you add and remove files. There's no pre-provisioning necessary. And there's no provisioning of either storage capacity or performance. It simply just grows in terms of capacity, and you get more throughput as you add more files, as we'll see in just a couple of seconds. EFS is designed to be scalable, which means that, again, without pre-provisioning, you can start in the gigabytes, go into the terabytes, and as your needs grow, it can get into the petabytes as well. And performance increases as the size used on EFS, on your EFS file system, increases as well. And it can support thousands of concurrent NFS connections across a wide variety of EC2 instances. As I mentioned earlier, the durability and availability is built into the product. And what this means is that EFS basically replicates your data across multiple availability zones within a given region. And so what this means is that in terms of durability, it is much superior to what most customers can create on-premise or do it yourself on EC2. And it's designed to be a tier 0 service so that you can create mission-critical applications on EFS and expect the performance, durability, and reliability that mission-critical applications require. So this is just an example of how EFS durability and availability work. Whenever you write a file to EFS, the data in that file is basically redundantly stored across multiple availability zones. So what this means is that if there's a service interruption in one availability zone, your applications will continue to work because EFS will be available from other availability zones. So what this means is that there's a wide array of different applications that can work with EFS. So workloads such as big data analytics, web application serving, home directories, content management are perfect for use with EFS. Now, EFS is a managed service. And so what that means is that there's really not much work that you need to do. The things that you need to do with EFS are, for example, creating a file system, deleting a file system, listing the file systems that you've created, tagging a file system, and creating mount targets. We'll talk about mount targets in just a second. And so you can do that via the web console, you can do that via the command line interface, and you can do that with the plethora of software development kits that we have for our APIs. So how do you create a EFS file system? You simply go to the web console, or the other options I mentioned, and within a couple of seconds, you have a fully available file system at your disposal. Once the file system is created by the service, you go to your Linux instance. If NFS is not installed, you install NFS, and then you simply mount the file system. That's it. So in under a minute, you can have a fully working file system connected to your Linux instance. It's that simple. There's really nothing else that you have to do. So when you create a file system, you'll see that it creates what are known objects what are known as mount targets. Mount targets are endpoints within each subnet across different availability zones within your VPC. What mount targets enable you to do, or your EC2 instances do, is connect to your EFS file system via a local IP address, an IP address that's local to that subnet. You can connect via IP address. You can also connect via a DNS endpoint as well. Now, this is just a small example of how you mount a file system. Hopefully, you can see that in the back, but the first line is I'm simply issuing a Linux mount command and telling it to mount the file system at the directory called EFS. That takes a second or two. And then I simply run the disk free command, and it shows me that I have 9.3 exabytes of data. Keep in mind that you're only charged for the data that you use, not for the data that's available to you. And that's all there is to it. Okay? Now, let's talk a little bit about EFS performance. EFS has two performance modes. One is a general purpose mode, which is the default and which is what we recommend to most customers. It is optimized for latency sensitive applications, and it's really the best option for most workloads. Now, if you want to get the most aggregate throughput out of your file system, there's another option called max IO mode, which can scale to higher levels of throughput with a little bit higher latencies. So for most customers, what we recommend is going with general purpose. There is a CloudWatch metric called %IO limit, and you can monitor that metric to see whether it's getting close to 100%. If it is, you can switch to the max IO mode. So how does EFS performance work? Well, EFS performance is based on two concepts. The first is that as a file system gets larger, generally it requires more throughput. The other is the observation that most file workloads are spiky. They tend to hum along at a certain baseline rate, and then during certain periods, they tend to spike up in terms of IOs. So what EFS provides is a scalable bursting model that's designed to make performance available to your application when they need it. And so it is represented by this particular graph. What this graph shows is basically the baseline rate that a given file system of a certain size has, and then the burst rate. The baseline rate is in blue, the burst rate is in orange, and what it shows is that generally you get about 5 kilobytes per second of performance per gigabyte. And so as your file system grows, the actual baseline rate grows along with it linearly. Now, the burst rate from 1 gigabyte to 1 terabyte is constant at 100 megabytes per second. But then after 1 terabyte, it starts to grow along with the size of the file system. So essentially, what this means is that as you start adding more files to your file system, the performance proportionally grows as well. Okay? Now, every bucket comes with 2.1 terabytes of burst credits, and so you have plenty of room to do workloads even if your file system size is in the gigabytes. So some bursting model examples. So if you have a 100 gigabyte file system, that means you can drive up to 5 megabytes per second continuously, or burst up to 100 megabytes per second for 72 minutes each day. If you have a 1 terabyte file, if you use 1 terabyte of storage on EFS, you can drive up to 50 megabytes per second continuously, or burst up to 100 megabytes per second for 12 hours a day. If you go up to 10 terabytes, you can see that the performance numbers increase by a factor of 10 from the 1 terabyte numbers that we talked about. So basically with 10 terabytes, you can drive up to 500 megabytes per second continuously, or burst up to 1 gigabyte per second for up to 12 hours a day. Okay? So where can you use EFS today? EFS is available in Northern Virginia, which is US East 1, Ohio, which is our new US East 2 region, our Northwest region in Oregon, US West 2, and then our Dublin, Ireland region, US West 1. And we have more regions coming in the near future. And so in addition to durability, performance, availability, pricing is also one of the main attractions with EFS. With EFS, the pricing is very straightforward. You pay per amount of storage used per month. So in Northern Virginia and Ohio and Oregon, it's basically 30 cents per gigabyte per month. And in Dublin, it is 33 cents per gigabyte per month. And if you're new to EFS and you want to try it out, we have a free tier which gives you 5 gigabytes per month for the first 12 months for free. Okay? So with that, and without further ado, I'd like to call up Austin, and he's going to dive in to what Spokeo has been doing with EFS.
Thank you, Saji. For those who don't know who I am Austin Fonacier. I'm the lead software architect here at Spokeo, and below is my contact information in case you want to send me hate mail. For those who don't know what Spokeo is, we are a people search engine. We're based out in Pasadena, California. Think Rose Bowl, Rose Parade. That's where we're at. Currently, we're hovering just over 200 plus employees. And to give you context over why we use EFS, the numbers are really important. So we get around 18 million unique visitors a month. We have over 8.5 billion people records in our data storage. And when it comes to Google crawling, we get around 30 million bot requests per 24-hour period. So Spokeo, the product, it's a people search engine, as I was saying. You can search for people by any intersection of data, whether it be first, last name, email, phone, etc. So to get to your person record as quickly as possible. Also on top of that, we've got products designed for people to be able to search by email or username or by an address. So again, to get to your person record as quickly as possible. So this is what our tech stack looks like today. So users come in through the ELB, they hit a Ruby on Rails cluster, and it looks like a usual tech stack where you got Memcache instances, you've got RDS, and then below that is a service. We call it a data service server. So the data service server is a JSON API that pulls from below that Elasticsearch, some really big Elasticsearch indexes, and then below that a really big DynamoDB cluster to house all our people data. And on top of that, data service will hit third-party services API looking for data to supplement so we have better data on our website. So if you pull up just a little bit, Spokeo just doesn't talk to one service, it talks to multiple services. So when you have a request for certain pages, the request isn't as simple as we make it out to seem. So this will be more apparent as we go through the slides. On top of that, we are an Amazon customer, so we have Lambda, Kinesis, etc. throughout our tech stack littered everywhere. So this is why I'm here. These pages are SEO pages. For this example, it's Dan Smith. We've got around 3 billion of these SEO pages. So that's around 37.4 terabytes of HTML. And then, as I was saying before, that's 30 million bot requests a day. So how do we serve these pages up as quickly as possible? And that's the answer. That's the question I'm going to answer today. So these SEO pages were designed for crawlers to be able to parse our full breadth and depth of data, and also for the users to be able to filter down to their exact record they're looking for as quickly as possible. So why the importance of page speed for these pages? There is obviously a page speed abandonment rate. So if we take a little bit longer to serve a page, people are going to go to our competitors looking for that same data. Google also utilizes page speed in their search rankings. So it's part of their metrics. So the quicker we serve up a page, the better we are in our search rankings. And then studies show a direct correlation between page speed and conversion rate. So if we serve up a page quicker, the better conversions we're going to get. So back to the original question, how are we going to get faster at serving these pages? One answer is we can tweak the Ruby on Rails stack to serve up these pages quicker. The problem with that is I've been with Spokeo for nearly 6 years, and I feel like I've tweaked the page to as fast as they're going to get. And so that last 10% of performance gain is really the last 90% of effort. And so it's just something that we didn't want to go down that route to really scrape the bottom of the barrel. Another option we came up with is like, hey, why don't we switch away from Ruby on Rails? Why don't we go with something a little more modern? The issue with that is that it's a ton of effort to really just dump your web framework and go with something new. And because of that, it's a ton of time for engineers to learn that new web stack, a ton of time to rewrite everything. Time equals money. And then the more important part is its unmeasurable performance gains. So what I mean by that is that if we're switching away from Ruby on Rails, we would have to go down this rabbit hole pretty far to measure that performance gains, what we'd be getting, and to sink a couple months into that project. So we looked over to a reverse proxy. So for those who don't know what a reverse proxy is, it's basically a thin layer that sits on top of your web stack that will cache and pull data on behalf of the end user. And that seemed most appealing for us because it was really a low amount of effort, some code and header tweaks, and immediately we can tell you how much faster data was pulling out of the reverse proxy versus our origin. So we looked at the over-the-counter reverse proxies like Fastly, Akamai, etc. They're all really fast. They're all really easy. Some DNS changes, header changes, and boom, it's up there. And on top of that, they had a global delivery system. So they had edge nodes where we wouldn't necessarily have our edge nodes. The one big problem we found with over-the-counter reverse proxies is the least recently used policy. So for this example, I have A through G in my reverse proxy, and below is my Spokeo web stack, as I spoke about before. And let's say, for example, I get a ton of requests for object A. Object A is really warm in that cache. C through G, it's all right. And then B, it's cold because there's no request for B. After a low amount of time, B gets dropped off the cache. And let's say I get a request for H. H isn't in that reverse proxy, and therefore we incur the penalty of going down to the origin for element H. And the problem with this LRU is that we lose the predictability. We lose that predictability of knowing at what point the 30 billion records, how fast each record is going to return. So we went back to the drawing board, and my CTO walks in through the door and says, hey, why don't we just serve Google the fastest possible page, and then leaves the room, as CTOs do. And Google really is our toughest critic, so by serving and pleasing Google first and foremost, we're really going to be pleasing our customers in the end. So we went back to the drawing board and we said, okay, what do we want out of this cache? We want it to be as fast as reasonably possible, as we always want our caches to be. We want it to be cost efficient. I don't want to spend money up the wazoo for this. I want it to be scalable, fault tolerant, and I want it to be available like 99.99% of the time. So one quick answer we came up with is, hey, why don't we store it in our web stack cache? But the issue is that there's an inherent penalty of going through that web stack to begin with. And we heralded back to our CTO and said, like, hey, we are really not serving Google the fastest possible page. And so we threw it out the window. So we came up with a two-part project. And I want to go over the reverse proxy first, and then I want to go over the backend. Where are we storing this 37.4 terabytes? How are we serving it as fast as possible? So this is our proposed topology. So end users will come in, they will initially hit the reverse proxy first. Reverse proxy will talk to some sort of backend that we dreamt about. And then also, if the data doesn't exist, the reverse proxy will hit our origin, our app servers. So when we were looking for reverse proxies, we looked at the open source reverse proxies out there, the heavy hitters, Nginx, Apache Traffic Server, Varnish. So all of them have a problem of having in-memory mapping of keys and values when we looked at them. So if you're trying to store, for our instances, 30 billion records, in memory we're carrying around 30 billion keys and values around in memory. And that, wasn't scalable for us. Nginx and Varnish were also at the enterprise level really expensive. And Apache Traffic Server doesn't notify other nodes of writes, at least at the time we were looking at it. So for example, if I have 2 Apache Traffic Server nodes, and all the traffic is routing through node A, and all this data is coming to the back end, node B has no idea all that data is there. And so we would have to figure out some sort of way of cloning Apache traffic servers around. It just seemed like a big mess. And all the code bases are huge because obviously these reverse proxies serve other purposes other than being a reverse proxy. So all of them have bloated lines of code. Most of them are really expensive, and the worst part was the in-memory key mapping values of all that keys and values. So as us engineers do, we decided to write our own. We called it mass cache. So mass cache, and I'll quickly glance over this. Now we have in-house expert knowledge of exactly what the reverse proxy is doing, rather than bringing in an Nginx expert or Apache Traffic Server expert, etc. And in the end, it's a very simple use case, which I'll talk about in a second. And it's inexpensive to run. It's a thin Node.js application. And best of all, there's no in-memory key mapping values. So this is what mass cache looks like in its barest form. You request for a page, do we have to cache data? If so, return it. If not, fetch the content from origin, and at the same time, return the data from origin. Hash that request query. So let's go back to our example of Dan Smith. We hash it, we come up with a key, and then we store that HTML in our storage engine under that key. So whenever time we have a request for Dan Smith, we know exactly where that HTML is going to be. So we solved that problem, and we turned our eyes toward the back end. We still have that problem of storing 37.4 terabytes of HTML, and we want it to be served as quickly as possible. How are we going to do that? We looked at a bunch of backends. So first we looked at S3 CloudFront, and because we're scraping for milliseconds, we saw a discrepancy in time, meaning if CloudFront, where it was in the edge node, and if it was warm in the edge node or not, we saw really fast or not so fast. Then we looked at DynamoDB. Dynamo was actually in our budget, and it was really quick. It's just we questioned whether or not we want to be moving around a database of that size to a bunch of, mass cache nodes. Then we looked at Elasticache. Elasticache, obviously, that size is really expensive, but really fast. And for us, wasn't data persistent. So if one of our Elasticache nodes went down, we were not exactly super confident we could get our data back up. Then we looked at EBS. The problem with EBS is that you can only mount one EBS volume to EC2 instance. So if we have 20 mass cache instances, we'd have to find some sort of way of cloning around EBS volumes and mounting them to each EC2 instance. And then Amazon approached us and asked us, like, hey, we have this preview coming out for this new product called EFS, and it may fit your bill. We looked at the cost, and the cost was very appealing. The performance was spot on. Let's talk about that. So performance, and these are effective performance numbers, 17 for reads, 30 for writes, and these are max I/O in the middle of the preview mode, like end of July sometime. And writes, they're effective writes. So for us, they were Node.js opens, writes, closes, reads, they're file descripting, etc. So I've been assured by Amazon that the actual performance of EFS is a lot better than this, but this is the numbers that my project managers were more interested in. And as Saji was mentioning before, there's built-in data redundancy. There's nothing we had to do to make sure that our 37.4 terabytes were redundant everywhere. It just handled that for us, and it was built-in scalable. I didn't have to worry about IOPS. I didn't have to worry about provisioning. Amazon literally handled everything for me. And as Saji was mentioning before, costs are based off of the amount of storage you're storing in EFS. If I got 10, 20, 40x the amount of traffic tomorrow, my EFS costs are static. And that value proposition for us was extremely appealing. So this is what our tech stack looks like today. People come in through an ELB, they hit a mass cache cluster. Mass cache cluster talks to EFS as our storage engine. And then if we don't have that data, we trickle down to our app servers to generate that HTML. And I get asked this all the time. How do we populate that 37.4 terabytes? Answer, we actively did it. We tried to actively populate as fast as possible. And as Saji was mentioning before, EFS really doesn't shy away from bursts. So we were bursting 250,000 requests per second. Let that sink in. That's really fast. So by that nature, we were able to populate 3 billion records in about 1 week. And updating that cache is really simple for us. We sent in a simple header and then updated. One lesson we learned by going through this process was if you're throwing 250,000 requests at your own web stack, you're basically DDoSing your own web stack. And so we learned the important lesson of dynamic throttling. So our dynamic throttling was based off of key metrics in our web stack, whether that be Apdex performance scores, response times coming out of certain services, or database load times. So that's a very important lesson to learn. So what are the benefits of living with this infrastructure for about a year? Cost to serve a cache page is significantly less than cost to serving a page from origin. Because our EFS costs are standard. Mass cache is simply a simple Node.js that spins up on a T2 micro, and it's horizontally scalable. Horizontally scalable. Let's go over these numbers again. I've been saying them over and over all the time. But 37.4 terabytes, 3 billion files, and then around 30 million requests per day. That's the definition of hopefully horizontally scalable. And now actively populating EFS really taught us about the bottlenecks in our web stack. If you're throwing 250,000 requests at your web stack, you're going to learn about the bottlenecks, and you're going to be able to correct them as you go around. EFS gave us something that I didn't think we would ever get, but offered us a lot of site redundancy and DDoS protection from outside. My job is to hound Google Webmaster Tools to figure out are we serving Google slower pages? Why are we serving Google faster pages? I'm hounding the engineers for plus 10, minus 10 milliseconds. But now with this, the predictability of how we serve Google, it's there. And so Google Webmaster Tools is flat as far as returning average response time goes. So you guys remember years ago when the cloud was a thing and we were promised like infinite servers in the cloud? This feels like the cloud for us. And after hearing a lot of talks about serverless architecture, this feels like that already. So EFS to us feels like an infinitely scalable resources. I don't have to do anything to get it to scale. It just scales for me. It's fast. And what I mean by fast, I mean my CTO is happy, which means it's fast. It's easy. As Saji, you saw Saji before, you just mount the EFS drive and then that's it. It's inexpensive. You're only paying for the storage you use. You're not paying for all this traffic we're getting. It's data redundant. I'm not worrying about where that data is or how it's stored. I don't lose sleep over it. It really was, for our problem set, the Goldilocks solution for us. So here are some minor lessons we've learned over the year. Writes, they're slightly slower than reads. So if you're trying to calculate to the second when you're going to be done warming the 3 billion pages, that's really important to learn. Writing a file is slightly slower than updating a file. So we were wondering when we were repopulating EFS, why was it taking a little bit longer? We found out, or writing to a new EFS cluster, why was it taking a little bit longer? now we know. Improvements have been made since the preview instance, such as NFS 4.1, which is really important for doing these things at scale. And I have all the reason to believe that Amazon will keep updating and improving on EFS. Any access to EFS call looks like a file call, but in essence it's a network call. And I think that's a really important lesson to learn. So the prime example was we had an instance where we were trying to read a file and serve it to our customer as fast as possible, but we were statting the file, describing the file, opening it, reading it. One of our engineers looked at that code and said, like, hey, why are we doing all that? And cut out all the cruft. And when that code went out, we were 2x faster at serving up these files. So if you're like me and we scrape for milliseconds of performance, that's really important lesson to learn. Saji was mentioning before, but general purpose isn't max I/O, and it's a very important distinction to learn. And so if you're looking for EFS in your stack, really look at the documentation, look at those metrics that CloudWatch offers, and determine which is for you. EFS offers us availability and stability like I haven't seen before. So there have been instances where key services would go down in our web stack, but we were still serving up these pages because EFS was always there and mass cache is a thin Node.js application. It was really nice to have. So one last important lesson we learned was way back when, this is very indicative of Google crawling patterns for us. They'd go from 0 to millions of requests in no notice at all. And so our web stack before would crumble underneath that traffic of Google. So we would meet the next morning, we'd decide, okay, let's 2x provision our servers to meet Google's need. And every time we think we'd hit peak Google would just keep throwing more traffic at us. And so we'd over-provision. And the problem with that is we're paying for all these servers that we're not using 99.9% of the time. But now with mass cache and EFS, we're able to serve Google up these pages because EFS just sort of scales for us and we don't have to worry about that. And scaling out a Node.js application, that's really simple. We've all done it. These are the related sessions, and I've attended most of them already, and they're all really good. And so what I've noticed that most of these sessions offer a different perspective on EFS, so they have unique problems that they solved with EFS, and they'll offer up another perspective on it, and they're all really, really good. And I promised my CTO I'd say this, but we are hiring, so there you go. There you go, Mike. And yeah, evaluations. Any questions?